Awesome. Hey everyone, thanks for coming out today. I'm Luis, this is Olivia, and we're about to dive into the fascinating world of imaginary numbers. Arguably, the cool side of math. So buckle up, we're going for a ride. So we were starting off in the early 1500s, way back when university math meets the streets. Niccolò Tartagalli, this man here on screen, a beautiful man, a math genius from the 1530s, shook things up with the groundbreaking discovery for a method for solving cubic equations. Later known as Tartagalli's poem, literally. Actually, let's just walk back a moment and appreciate this man's poem writing skills. That's the whole poem, translated in English, and I'm going to take on a 3-minute tangent to read about it. When the cube and the things together are equal to some discrete number, find two other numbers differing in this one. Then you will keep this as a habit, that their product should always be equal, exactly to the cube of a third of things. The remainder then, as a general rule, of their cube roots subtracted, will be equal to your principal thing. In the second of these acts, when the cube remains alone, you will observe these other agreements. You will at once divide the number into two parts, so that one times the other produces clearly the cube of a third of the things exactly. Then of these two parts, as a habitual rule, you will take the cube added together, and this sum will be your thought. The third of these calculations of ours is solved with the second if you take good care. As is in their nature, they are almost matched. These things I found not with sluggish steps. In the year 1504 and 30, with foundations strong and sturdy, in the city girdled by the sea. All right, I swear it sounded better in Italian. But now back on topic. His approach marked a shift from numerical examples to abstract reasoning, paving the way for a more systematic approach to cubic equations. Now let's get into the nitty-gritty. Tartagalli's method, involving two numbers, u and v, ingeniously found their sum and difference, as described in the poem before. He shared this method with Girolamo Cardano, the man on the left of the side on the screen, in 1539. It became Cardano's formula for the depressed cubic, despite some shady circumstances surrounding its publication. Girolamo Cardano, more famously known as Girolamo, a bit of a character in mathematical history, incorporated Tartagalli's method into his grand work, Ars Magna. Unlike Tartagalli's systematic approach, Cardano's method was presented as a quote-unquote recipe, creatively defining x in relation to a three-dimensional cube, introducing a more generalized form. However, challenges arose, especially with new forms of cubics, leading to solutions containing negative square roots, as the example shown. Cardano's work laid the groundwork for the introduction of imaginary numbers, setting the stage for further exploration. Now we meet Raphael Bombelli, this Chad on screen. A pragmatic mathematician, despite lacking formal training, that's a big flex, made significant contributions with his work, Algebra. Bombelli introduced a new language for imaginary quantities, coined terms like I meant PDM and MDM. His genius extended to changing imaginary expressions, providing an ingenious proof that any real number can be expressed in complex form. This marked the beginning of complex numbers as linked radicals of a new type, laying the groundwork for further developments in algebra. Enter Gottfried Wilhelm Leibniz, or Leibniz as some call, a German mathematician and philosopher. Leibniz explored interesting properties of complex numbers, noting that linear combinations of conjugates resulted in positive rational numbers. Despite using the term imaginary, Leibniz remained uncertain about the nature of complex numbers, viewing them as distinct from real numbers. Now, I will let my Olivia continue.
Leonhard Euler, mathematical minds in history, made foundational contributions to various mathematical fields. Euler introduced the symbol I to represent the square root of -1, providing a concise notation. Despite this, Euler, like many of his peers, perceives complex numbers as non-existent, suggesting that their use indicated an unsolvable problem. As the 18th century progressed, mathematicians began exploring different orders or types of complex numbers. D'Alembert's work in unifying various forms of complex numbers into the expression a plus bi provided a clearer framework for their study. Furthermore, John Wallis attempted to represent complex numbers geometrically, introducing the idea of an imaginary triangle. However, his work lacked widespread acceptance due to unclear notation. William Rowan Hamilton refined this concept, proposing an ABI coordinate plane to represent complex numbers as ordered pairs. Our journey today culminates with Carl Friedrich Gauss, a leader who tackled the fundamental theorem of algebra. Gauss's direct and abstract proof demonstrated that an instable equation cannot have more than n roots. His cautious approach towards imaginary numbers highlighted the need for rigorous proof, challenging assumptions made by his contemporaries. In conclusion, the development of complex numbers was indeed a complex process, evolving over centuries and involving brilliant minds who grappled with the conceptual challenges posed by these mathematical entities. Complex numbers, far from being a mere curiosity, have become an integral part of our mathematical exploration, enriching our understanding of algebra, geometry, and number theory. Thank you for joining us today on this wonderful journey.